Today we are going to do section 5.4. Sorry, what am I saying? Section 1.12 on page 55, actually. Okay, so first I want to scan our books. And let's see, yeah, that should be it. A little closer on top. And then a little bit on the bottom. Okay, that's page 55. Next, page 56 and 57, which has, what am I doing? Okay, the full page first. Okay, and then the top, a little closer on the top. It's not focusing very much. Oh well, and then on the bottom. All right. Okay, next, page 58 and 59, the whole page. All right, a little closer on top and on the bottom. Okay. And finally, page 60 and 61. As you notice, we're coming to a new chapter. Very exciting. Okay, yeah, that looks, I guess, tolerable. And then a little closer on top. Okay, and then on the bottom. Okay, that that should be it. So let's start with the page 55, okay, implicit functions. Now we have done some implicit functions in this chapter, but now we're going to go into the explicit proof of the existence of and the uniqueness of the implicit functions. So first, let's look at some example. Okay, we have let's say big F x y equal to 0, and we have three situations. What if big F equals to x squared plus y squared plus 1? Now then there are no real solution to this because, well, anything that is being squared plus 1 is not going to be equal to 0. Okay, and the second option is what if big F equals to, I'm talking about this part, right? And what if it equals to just x squared plus y squared? That has a solution at the origin only. And finally, what if it is big F is x squared plus y squared minus 1 equal to 0? Now, in that case, we do have a solution, and that is the circle here, the unit circle. But there is a problem to that, and that is this big F is defined at 1 up to 1 and minus 1, but no further. That is, one doesn't have a two-sided neighborhood where the F is defined, okay? And that is, for example, for 1 is defined here, but not on this side. So, and we want a two-sided delta neighborhood. So this function is unsatisfactory. Now, in this case, you might also want to notice that the partial derivatives at these 2 points are 0. The f2 is 0 here, and f1 is 0 here. Okay, and that means something, as we will see right in this section. Next, let's look at the existence theorem. Okay, we are at the bottom of the page. We're going to show that if f of xy equal to 0, but f2 is not 0, and then we can solve y for x. Notice that f2 is partial big F against partial x. Partial y, right? That's what f2 is partial f, partial y, which means that if we want to yank y out of this mess, implicit equation, we will take the partial big F, partial y to get it. Similarly, this theorem also works, of course, if it's x that we want. If we want to pull x out of there, then we need to check the partial big F partial x, that is f1 is not 0. But we'll think about that later. Right now, let's focus on one thing at a time. That is f2 is not 0. Please turn to the next page, theorem 14, where we have the theorem stated as we have a big F which is belong to C1, and that's going to matter. Okay, so and then we'll set the whole thing as to be equal to 0. If it isn't 0, we'll just move the stuff to the other side of the equation sign and define big F as 0 anyway. Okay, so big F is always 0 as a result. And then we'll specify the F2 is not 0 in this for this proof. But of course, F1 is no different, right? They are completely the same thing. And so F2 is not 0, and because it is F2, then we will be able to prove that there exists a unique function f. So we can plug y out of it, and that equals to f of x, such that is f of x0 is equal to xy, and f of x and y equal to f of x will solve this equation. In other words, if you plug f of x as y into the big F, everything will become 0 at the proper neighborhood. First we remember that this is defined in some neighborhood that can be small, okay? We're not greedy here. We're just defining for one point at a time at a little neighborhood. But if all points satisfy this solution, then we got the entire neighborhood included. But for now, we'll focus one point at a time. So then because we are focusing on one point, then we find even a smaller neighborhood, okay, and at the eta neighborhood. So that thing there is pronounced eta. At least that's what the internet says. And so that we can find a tiny neighborhood where, tiny but existing, okay, where we can do this inverse function trick. We can yank y right out of there where everything fits. And more importantly, this function that we yanked out is also going to be C1. That is, it has continuous first partial derivatives. And we'll prove all of those things right now. Okay, so first we assume that F2 is bigger than 0. And then what does that mean? Then that would mean the F2 is bigger than half of F2 at the x0, y0. Now that, being that it's bigger than 0, that is not hard to imagine, right? Right. And in the delta, so we just yank that out and assume that that's the original delta neighborhood. That is, if you have a function that's bigger than 0, say, like this, say we have a function running around and it's bigger than 0 in a small area, okay? This is a delta neighborhood. Then we can assume then it's bigger than some other number in this neighborhood. And where part of it, okay, this is fx0. The one point where y0, then we can assume that in a small neighborhood along this point, this whole thing is bigger than half of it, okay? And so, and that is that we will prove in the homework section as well. But that is intuitively clear that it is up there, right? So you can cut it in half, and with a small enough neighborhood, it still should be positive, bigger than all of that stuff. And anyway, so we'll prove that in the homework, but right now we'll just believe that. Now that will be, so F2 is going to be bigger than half of its value at the x0, y0 in the entire delta neighborhood we're talking about. So if F2, remember F2 is partial derivative with respect to y, which means the function at x0 but y increases is a strictly increasing function because its derivative is positive, okay? We're assuming the F2 is bigger than 0. So its derivative is positive for in the delta neighborhood of y. Okay, that is y minus y0 is less than delta. At this point, then we can then say that therefore on the positive side is that big F is going to be bigger than 0, and on the negative side is going to be less than 0. So this is only talking about in the tiny little neighborhood, okay, where this increasing happens. And because big F is continuous, then we can also argue that this is true for a small neighborhood of x in this range. That is, as y goes from from in this little neighborhood as y value goes from y0 plus delta and y0 minus delta, there's a x neighborhood. We call it within the x0 a little eta neighborhood when f is also bigger than 0 and the plus side and less than 0 in the negative side. Okay, and so now we have this graph that we're looking at where things are, well, please look at this graph carefully until it makes sense to you. So basically, this is x0, y0 right here, okay, where the value is, where the y value crosses from negative all the way to positive in a very small neighborhood where the y value is strictly increasing. Now, if that is true, then we can find a little x value across where this fact stands. Okay, that is, as y crosses here, it doesn't necessarily cross here. It might cross somewhere else, but it will in this little neighborhood. It will cross. All y values in this x neighborhood will cross from negative to positive, okay, in the graph, so in the 3D graph, that is. And so we the next thing we must focus on is that the continuous function passing from positive to negative values must pass through 0. Now that is, you might remember the intermediate value theorem, right? You go from positive, you have a function goes from positive to negative or the other way around, it's going to cross the 0 point. But we'll prove that in a later chapter, okay? But for now, we'll just believe it. So therefore, for each x in the interval, there must be one and only one value of y. We're proving uniqueness here, okay? And both existence and uniqueness. So there's a one value of y, which we call f of x, which is between the y0 minus delta and y plus y minus delta, where the f of x each is 0. And that is the line we're drawing here, okay? As y value goes from, see all the negatives down here, and y value goes from down here, it eventually becomes positive when it got over here in the little eta neighborhood. So it has to cross. It might cross at a different point. See, it might cross here or down here or whatever. But it will cross at just one point to the other side as the value, f value increases from negative to positive. Now the point is, and also the reason we call it unique is because we can, if there are two values where the function is 0 again, then by Rolle's theorem on page 9, then remember Rolle's theorem says if you have a function that crosses 0 and then come back and cross it again, then it has a slope of 0 at some point, right? So then, but we already assume that the slope is bigger than 0. Okay, f2 is bigger than 0 in our little neighborhood. We're only thinking about a small area here. Okay, our focus is just on a tiny little point where everything is nice, and f2 is positive all the time, so it cannot be 0, which means this function cannot dip back and dip through 0 again. It only crossed 0 one time, and therefore the value of y is unique, and our function f is well defined because functions can't take two values. Okay, so now our function is properly defined, and so that what's left is for us to prove that the function is somehow differentiable. It has continuous first derivatives. So let's, but before we prove that, I want to show you a graph I drew of this situation, okay? Now, look at this is a 3D rendition of the big F, okay? Now, as you can see, the big F rises from the bottom and then crosses into the top. Where it crosses the xy plane, that's the equation, the intersection, the red line, that's y equal to f of x. Yeah. Okay, so as you can see, it dips below and it crosses at x0, y0. That's the intersection of those two, the purple and the green lines. Okay, that it crosses there, exactly there. And at other places, it might cross here, there, whatever. Okay, this is just a very small neighborhood of x0, y0. So it crosses x0, y0 here, and the rest of the places are a little differently. But as you can see, the function in this tiny little area, it rises from being from negative, okay, below the x-axis, and rises to the positive. So, and then it goes all, and then it does whatever, okay? But we're only focusing on a very small area of x0, of the neighborhood of x0, y0, which you can see how the function might go up. And I plotted that because I like the Desmos 3D calculator. You don't have to do that, okay? Because the goal actually is to be able to see this without plotting it. But I thought, you know, why not plot it? It looks so cute and so easy to plot. But that is the idea of this thing, okay? So this is the ground map, and you imagine the function f dips below. This is the xy plane. So the function dips below the xy plane here, okay? And it's strictly increasing in this direction, in the y direction, until it rises all the way above. And that's how this theorem is based on, the concept, which is pretty neat, actually. So now let's prove this thing is C1, okay? It's not just, it's differentiable, and not just differentiable, but that is continuously differentiable. And we are going to do that is, well, first we should check that conclusion A is true, because that's how f is defined. F is equal to y0 at x0. And then to prove, and B, of course, is also from f's definition. F satisfies the condition that you will, where it equals to f of x, and then that is condition B here. And when you plug f in there, then big F is along here is where big F crosses the 0 point, right? So big F is 0 in the entire little neighborhood, where if you plug in fx as y. So in other words, y is the solution to the implicit function. Y equal to f of x solves the equation big F equal to 0. Okay, that's what we are striving for. Now the next thing, we have to prove that small little f is C1. To do that, we will say that we'll pick some point, and we'll pick a point y1, which equals to f of x1, okay, at this point in the book. So which is fine, and then we'll pull out that this is all in the right neighborhood, okay? Remember, we have everything has to be within that little eta neighborhood, which is fine. We'll just, so we'll pick pick y1, which is x1, and then of course y1 plus delta 1 will be equal to f of x1 plus delta x. And then we plug this into the big F. Let's plug it into the big F, okay? In this line, we are plugging things into the big F, right? And what happens when you plug into the big F? By the equation 2, equation B on the other page, yeah, there. As you can see, if you plug it in, big F will be equal to 0, because that's how we constructed the function f. Therefore, we have right here the first sentence. The big F of f1 delta x, y1 delta y, being that y1 is a function of f, that equals to 0. Okay. And secondly, we're going to pull out the law of the mean, okay, from 10 pages ago. And it's copy and pasted right here. And you might remember the law of mean says something about theta, right? And a function is equal to f1 and then theta delta x, etc. And then f2 similarly, and as is shown here, which is good. But here's where our trick happens. Okay, now if this is true, that means the long equation right here equals to 0. Okay, and what does that? It means a lot. Now that means, I'll write it out here. Okay, that would mean that this whole thing equals to 0, which means f1, okay, blah blah blah, delta x was equals to negative of f2 delta y, right? Because this whole thing equals to 0. I mean, when you put it on one side. Okay, now if that's the case, then as delta x go to 0, we'll let delta x go to 0, And that would mean that delta y is going to go to 0. Why? Because we already said that f2 is not 0. That's one of the conditions in this little neighborhood. So delta y has to go to 0. That is, all right. And then the first factor of, let's see, this term, yeah, but you can also argue, however, this term might be bigger than 0, but what if it approaches 0? And so that's where our condition, a little earlier, we had the condition on the previous page where f2 is always bigger than a set number, a positive number, right here, okay, where my finger is, see? It says f2 is always bigger than this number, f2 x0 y0 over 2, which is positive. So this thing can't even go to 0. It's always positive in what we're talking about. So therefore, delta y will go to 0 because delta x goes to 0, forces this side to disappear, and that doesn't disappear, so delta y will go to 0 as delta x go to 0. All right, so then now at this point then we can now do something like this. We'll do this, the next equation is then delta, I'll write it on this side. Okay, as a result then delta y by delta x, oops, I'm writing d here. So as a result, delta y by delta x is equal to the negative of f1 divided by f2. Okay. Let's see. All right. As delta x go to 0. So if you let delta x go to 0, okay, I will show it to you. Now, from this equation, if you write this thing out, as delta x go to 0, so then delta x disappears in here, and then delta y also go to 0. So by the time you take the limit, that equals to this fixed number, right? And f1 and f2 are continuous, so you can let things go into 0 in here, and you end up calculating the f prime at x1 is exactly this value. In other words, f prime exists and is equal to a set number, and that's how we prove that the function f is continuous, and which means that the function being the f1 and f2 are continuous, right? And so then the f prime is also continuous, and as a result, the f is belong to C1. Yeah, I should say that because f1 and f2 are continuous, and so this quotient then is a continuous function of x1 and y1, so everything is continuous. Okay, so then we have succeeded in proving that f is actually C1, which I thought is kind of neat. Now the next sentence we say we're not going to prove it, but we're going to say that we prove this thing for just 2 variables, but if there were 3 variables, then this theorem applies as well. Okay, and we're going to do it with similar conditions, except that let's say you want to solve for z. That's the 3rd variable. Then you will take f3. That, in other words, you will check that f3 is not equal to 0 at the point in question, and then we will use the theorem to say that therefore is able to plug z out of there as a function of x and y. And so this part is important. Okay, so pay careful attention to this 3 variables situation, because we will mention it several times in the rest of this section. So please read through the proof of theorem 14 yourself as well. Okay, make sure that I didn't miss anything and that everything makes sense. Now continuing on page 57, let's consider the next section, functional dependence. Now 2 functions are functionally dependent if you have a very interesting situation. Consider, for example, these 2 functions. We have f equal the sine of this stuff, g equal the cosine of the same stuff, then there is a big function f of z of only one variable, such that if you stuff the small f into big F, it will come out with g. Okay, and just by even looking at it, you can totally see what big F might be. It just, well, we'll just take out the cosine and slap on the sine, right? And which is what it says right here. Okay, here is a big F is equal to cosine inverse sine, and that will work. Now, in the meantime, for that particular function, if you were to calculate the Jacobian, you will end up with something like this, and you will quickly notice that the Jacobian equal to 0 all the time. In other words, identically 0. Now, this is a specific situation that is common, that is characteristic of functional dependence. Now, so let's look in the next theorem. We're going to consider a criterion for functional dependence. First, let's consider this part real quick. Now, if f and g are functionally dependent, that is, that thing works, right? G equals some big F and of little f. If that is the case, then we have, that's equation 5. I wrote it up there. But if you do this math real quick in your head, then G1 will be big F prime, little f1, and similar to G2. So when you calculate this Jacobian, so you have f1, f2 down here, and then G1, G2 over there, okay? And if you look at it for a second, you'll notice quickly that that thing equals to 0, because the cross multiplication and subtraction is the same. And so then, so that establishes that anything that's functionally dependent, it absolutely has to have a 0 Jacobian. And so now we are going to have some other look at theorem 15, which says that if we have two functions, f and g, that belongs to C1, and then their Jacobian is 0 with respect to x and y, which is what they're dependent on, and then say one of the partial derivatives is not 0. We'll choose f2 in this case, but there's no reason to choose f2. It could be f1, g1, g2, they're the same, okay? But for now, for the convenience of proving this theorem, we'll choose f2, but you can apply to the others as well. Accordingly, maybe shift a few variables around, okay? And this is true in some delta neighborhood of x and y. So then, well, anyway, these are the conditions. Well, what about it? Then, if these conditions are true, then there exists a function big F of z and some number eta. So in that eta neighborhood where what we wanted does work. That is, gxy equals the big F of small f xy. So this equation will work, okay? That is, we'll be able to find a function big F to be able to pull this off. In fact, the proof of this function is exactly how it also shows you how to create this big F, okay? Which you will need to do in the homework. So look at this example very carefully. I mean, look at this proof very carefully, and then you will know how to do and not just how to prove it, but how to do the homework as well. So I wrote down the proof here, okay, scanning the book and rearrange some of the things because I feel that it makes it easier for me to explain stuff. Now, first, let's review theorem 14, the one that we just covered, but except for 3 variables. Remember that in this case, it states that at the end of the theorem proof, it says that if for 3 variables, you can still solve for, say, z, okay, if you know that it is 0 at some fixed point for x0, y0, z0, and the third, and the partial derivative with respect to z is not 0. That is, whatever you are solving for, you need to make sure that the partial derivative with respect to it is not 0. All right, so that's theorem 14. And then, so with that, bearing that in mind, please memorize that for the next 5 minutes or so, or 10, and so that we can get through theorem 15, because we're going to need it. So theorem 15, I have the conditions that I just mentioned, okay? Well, anyway, so let's get to the proof. First, we are going to right here. Okay, here are the conditions. Now the proof is, let's say z0 is fx0 and y0. All right, and then what is g of xy0? Well, I called the big G as fxy minus z equal to 0. I feel, and well, the book doesn't do that, but I feel that make things a little clearer. Okay, so then by theorem 14, well, and g of x0, y0, and z0 is 0, of course, because of this. Okay, and then I'll take the partial derivative at g2, which happens to be f2, and that is not 0 as given here. So therefore, by theorem 14, the one we just looked at, g can be solved for y. So right now we're focusing on y. Okay, so we'll yank y out of there according to theorem 14, and we're allowed to do so. We'll yank y out of there, and y is some function of phi of x and z. And this specifically, this thing will be able to solve solve that equation. If you plug y in there, it'll solve that equation over there. Okay, and so far so good. And so y equals phi of z, and it specifically solves the equation f of xy minus z equal to 0. Now, so next, let's do some partial differentiation. We'll take the partial derivative of this thing with respect to x. Then we get this f1, f2, etc. And very soon you come out with you can plug partial y, partial x out of there, which is phi 1, by the way, because y is defined this way. So that equals to phi 1, which is end up being minus f1 over f2. All right. So then secondly, we're going to calculate this thing. What was g again? G is just one of the functions that was given in this theorem. Okay. See, g is in C1, and it was given to us as the premise. So now we're going to plug this phi that we just calculated. We're going to plug the phi right into G1. Okay, right into G, and then we'll take the partial derivative of this whole thing with respect to x. Now, so if you apply that, then you will end up with something like G1, G2, phi 1, etc. Okay, if you look at it carefully, you check that does make sense, which then we'll do. What is phi 1? Remember, phi 1 we just calculated is actually negative f1 over f2. So I plug it in here, rearrange stuff a little bit, all right, and found out that ended up being, what is that thing over here? Notice the stuff in parentheses, that's exactly the Jacobian. Okay, and remember that one of the conditions is that the Jacobian is 0, which means this partial derivative right here equals to 0, okay, in this required neighborhood and stuff, of course. So now we have calculated that the partial derivative of this g with x and phi is identically 0, is 0 all the time, which means we can integrate it, okay? And if we integrate it, then this function is based on, equal to some big F based on z only. Now that is a very neat trick. In other words, what happens is that being that this function of g, when you take the partial derivative with respect to x, it is 0 all the time. This function is not dependent on x. It only depends on z, and therefore, which is why we can rewrite this function as a function, a big F of z. Okay, now this is how we are going to come up with a big F in your homework. Okay, so focus on this part very carefully, and that's how, when you do your homework and you're supposed to find the function big F, and you have no idea how, look at this stuff very carefully, and it will tell you how. All right, and so we have the big F here, which equals to g. Now at this point, what we're going to do is we're going to plug all the stuff in. Now, what was z again? Z is equal from that equation that we have earlier. Z is f of xy, right? And so we plug it into the big F. And then phi, what was phi again? Phi is y, right? And we have it a little bit earlier. Yeah, see, phi is y. So we'll plug it in here. So we're plugging in G where phi is y. And then what do we have? We have this thing, which is, what is that? That's exactly what we're looking for. That is, G of xy is some big F and then you stuff f of xy in it, okay? And big F is the function of only one variable z, and therefore we have concluded the proof. Isn't that neat? That is, again, remember to pay attention to this part of the proof very carefully, okay? Because that's how you're going to do your homework. Because in your homework, you will be required to figure out what big F is. That is, if you're giving two functions, f and g, okay, and then they're supposed to be what? Codependent or something. What is this called? Well, whatever they're called, okay? Whatever this thing is called, you will be given two functions, f and g, and you will be required to figure out the big F such that this relationship holds. And the secret to doing that is inside the proof itself. Follow the proof, and then you'll be able to find it, no problem. And so that is that's that. Next, let's continuing on page 59, simultaneous equations. First, let's talk about some kind of a neighborhood. Okay, we have a point. We have a point with four coordinates: u, v, x, y. At some point in 4 dimension, and then we need some kind of a delta neighborhood. Okay, where u is within delta of u0, etc. So all 4 variables within delta of the original point. The point being this thing, okay? And there's a name for this thing. We'll call it a delta neighborhood and delta of all those 4 things. And so that is a quick new notation. And with that, we are able to prove Theorem 16. Before we prove that, I want to mention Theorem 14 again, okay? Now this time, please pretend that there are 4 variables, being that Theorem 16 has 4 variables. Pretend there are 4 variables, but nothing changes, okay? That is, if you need to solve for one of the variables, then at a specific point, x0, y0, z0, and some other thing, 0. And then what you do is that you make sure that the partial derivative with respect to that variable that you're doing is not 0. And if you do, then you will be able to yank that variable out of a function of other variables, and it will be C1, and it will be unique. All right, and so that is Theorem 16. Now first, let's look at Theorem 16, which has a bunch of stuff. Okay, Theorem 16 states that we have a big F of 4 variables, small f of 4 variables, all in C1 in that delta neighborhood that we mentioned, and then big F and big G, big F and big G are both 0. Now, to explain what that means, why is that a simultaneous equation, I have written down in red here. Here's a sample that you can look at. So here's a sample of a bunch of x, y, u, v's together equal to 0. And then somehow you add these equations, you're going to supposed to be able to solve u and v in terms of x and y. Okay, and that's what this theorem is about. Now, so then we have the conditions here where there exists a unique pair of functions, f of x and f of y. Okay, where is that? There exists, unique pair. Where's my function? Yeah, in the middle. There exists a unique pair of functions fx, fg, xy, positive number eta. That's just for the neighborhood. So we have a tiny little neighborhood, eta neighborhood, where all the stuff we're looking for exists. That is, the functions f and g will belong to C1, continuous partial derivatives, and then f of xy will be equal to u, and v will be gxy. In other words, we can plug u and v out of the xy business. I mean, out of the big F and big G. Okay, so that is like we normally do by solving simultaneous equations. In this case, it's a simultaneous equations of 2 equations, and we're plugging out 2 of them at the same time, leaving the other 2 as independent variables. And so that is that's the goal. And remember, for this theorem, that the Jacobian of f and g against u and v is not 0. In general, we need to, whatever we need to get it out, like in this case u and v, we need to make sure that the partial derivatives or the Jacobian is not 0 at the point in question. All right, so let's now that I've said all that, let's look at the proof. Now the proof says because the partial FG partial UV is not 0, then the FU and FV can be both 0, right? Otherwise the Jacobian would be 0. So then let's say FU is not 0, then there exists some kind of a function, I'm quoting theorem 4 now, okay, that because FU is not 0, this satisfies theorem 14, which means we can plug U out of there, where as said here, U equal to, let's say, HVXY. So we can plug U out of there in terms of the other stuff, which will solve the big F. So far, U solves the big F. Okay, so far so good. And then now, so we already plugged U out. Now, the next question then is how we're going to plug V out. So, but U is only in terms of V, X, and Y. So we're not done yet, okay? Because we need U to be a function of F, which is dependent on X and Y only, whereas V, we need to yank V out as well. But so far, we've taken one step, and that's a great step. Okay, and so let's continue. Now, next we have partial F, partial V. To do that, we are going to see the F right here. We're going to take his partial derivative with respect to V, okay, with H in there instead of U. So if you do that, then you get to this equation, which calculate the HV then is equal to negative FV over FU. Okay, so far so good. So that's the next step. And then thirdly, we are going to do something called, we're going to solve this with big G. So let's call big G in, and we'll plug the HVXY in there. And the V, So HV, what was H again? H is something we just solved. Okay, that H which represents U, is going to solve the function big F. Okay, so we'll plug that in, and so now we have a G, and then and we're going to do something to this. Okay, by what? We're going to take the partial derivative, of course. Now this time we're going to take partial derivative with respect to V, which gives us that thing, and we rewrite it a little bit. We very quickly will recognize that A equals 1 over F of FU, and then partial FG and partial UV. Now that is, remember, that's one of the conditions that the Jacobian is not 0. Okay, and so then this whole thing, partial G, partial V, then is also not 0. Then so we're going to slap on theorem 14 again, which means that we can pull V out of there because we are doing the partial with respect to V, and it's not 0. So we can yank V out of this thing right here, and V will be V equal to G of XY, which will be a function that solves this big G. Why is V only XY? Because right now in this situation, there is no U in here, okay? There's only V, X, and Y. That's it. So when you pull V out, there's only X and Y left. So that's how we're able to find the unique G, which belongs to C1, and V equal to GXY, that solves this thing exactly. All right, so we are doing great. Now we are going to set F equal to, so we have already figured out H, right? What was H again? H was U, right? And then we're going to plug this V, which is only in terms of XY. We're going to plug it into the H. So now H is going to be called GXY. And we'll call that F. Okay, so at this point, therefore, being that H, we already said that H and G are unique and in C1, then F is also C1, since F is, well, H, right? And a combination of H and G. And also, the big G of FGXY, as we have shown, that's equal to 0, because we already showed that V solves the big G equation, and H, of course, being F, also solves it. So everything solves, and then the three conditions of the theorem are all satisfied. Now please take a look at that again and to see why they're all satisfied, because we mentioned that F and G are in C1 and they are unique and stuff. Okay, so that comes to the end of this section. For homework, let me find it. Now, for this entire section, please be sure that you go over it yourself as well to convince yourself. And this section is slightly more confusing than the others because when you prove implicit functions, you have to go back to the original one. And what are we proving? And it can get lost fast. So, but if you write everything down carefully, okay, and make notes to yourself, what's the original function, what are we solving, and all that stuff, it does come out eventually if you give yourself time to look at it, which is what I did. And so let's look at the homework on page 60, where we are going to do problems 1, 2, 3, 4, 5, 6, 8, 10, and 11. All right, so please go do that, and when you're done, I want to talk about them. So homework on page 60, I want to talk about, well, problem 1 first. We have, what are we doing? We are having a situation where I guess we just go ahead and calculate the whole thing out, applying theorem 14. Everything comes out, I think, fairly nicely. Okay, and at 0, 0, being the F2 is equal to 0, then we're failing the condition 3 of the theorem, and therefore there is no little, you cannot pull out some F that will make it work. But otherwise, everything else works okay. All right, so, and then problem 2, we're proving, well, we're using the delta epsilon proof, okay? And that's on a that we covered earlier in this chapter. So what we're going to do is just use the delta epsilon proof, mostly right here where we have f of x minus f of x0 is less than f of x0 over 2. So that, by definition of the absolute value, means it's less than the value itself and bigger than the negative value. Then you just slap this f to the other side of the inequality, and this thing will come right out. So, and problem 2 is a preparation of doing problem 3, which is very similar to problem 2, and except that it's in 2 dimensions. And then, but the story is the same, okay? And I wrote down C page 12, if you can remember the delta, at least I think that's what that means. It's the delta epsilon proof. And so we have, we will choose, we have, well, f is continuous, of course. Then we have, we can choose the epsilon, which we will specifically choose it to be that thing, okay? And following the delta epsilon definition of continuous functions, we will come up with the same thing as problem 2, this inequality, where we then slap that negative sign over here and to become positive, and this equation, this solution comes out right away. Next, let's look at problem 4. We have f and g, and we need to find that, what is that called? I can't remember what those things are called. They are, seriously? But whatever, okay? The point is, we're trying to do this, right? Well, where g is big F of small f, and big G is, small f is the big G of small g. Is what we're gonna do. I'll figure out what it's called later, which is in, this is shown demonstrated in theorem 15 on page 58. So that's what I did. Now we'll follow the proof of the theorem, okay? And then at first we need to figure out what x0, y0 is. I don't think the book gave anything, so I just made something up. Okay, we'll choose x0 to be 1 and y0 then equals to 2e. And then we have this equation, just like the way the theorem is proved. And then we have, then I solve for it. Eventually, I have to plug x out of there. And that will be at x equal to 1, z equal to e. All right, and that we'll call it phi, just like the proof says. So phi yz is equal to this thing. And then continuing, we have, well, we'll do G later, okay? Right now we're focusing on F. So then we have x0, y0, and z0, and then I wrote down the G, plug it into G, we get this thing, and this is big F, Okay, you just have to, once we solve for x, for phi, you plug it into G according to the theorem. This is exactly big F. So big F equals to this stuff right here. And by plugging into the x in terms of z into the G equation. So then we have G equals to, G equals to that. And then when we plug it in, then so we solve for big F, and then I confirmed it here. So when you plug in small f into big F, you get the stuff, and that's eventually equal to G, okay? Because that's what G is, so that my big F is correct. And similarly, we're going to calculate big G the same way. Let's see, yeah, on the following page. That is, we follow the same pattern, okay? And then eventually we have to solve this thing for x. And so I pulled out the quadratic formula, I believe. And then I only kept one of the signs because the other one doesn't work for my point, okay? I chose a point, convenient point. I chose 0, 0. So then the whole thing is, the whole thing being at the origin, and the plus 1 works. So that I will choose that for our phi. And then I have, to write the e function easier, I have at times write the exp to represent e, okay? Just to write things a little easier. So I have things plugged in exactly the same way. And then when I double check it, it does work out. See, G of big F, what was G? G is this thing right here, which is the E of all that, okay? And then when I double check to plug things in, it does equal to, one does equal to the other one. That is G of GX over here does end up equal to f of x, okay? By the time you get through some minor algebra. So that works out very nicely, and that's problem 4. Problem 5 is if you have two partial derivatives is constant, then the function will be, two partial derivatives equal to 0, then the function has to be constant. Well, the reason for that is you slap on the MVT from page 46, that is the MVT for 2 dimensions, mean value theorem, and you soon notice that the f value of 2 different values of f is always constant. The 2 different values, the difference between any 2 values is always 0, which means that they're the same, which means the function is constant. Okay, yeah, that's that. And I think the next problem, problem 6, is similar. Somehow you slapping on now you slap on the easier MVT, the mean value theorem. That's the one on page 9. And you notice that because the derivative is 0 all the time, then the 2 values are the same, which means if they are always the same, then we will define it as a phi y, okay, which is the same as y value at 0. Because the function f does not depend on x. Okay, now I remember what they're called. Let's look at problem 8, functionally dependent. I think that's what it is, right? Yes. So we're going to prove that f and g are functionally dependent. Now f is a simple enough problem. G is much longer and tedious, but we can do it. But it doesn't work out so poorly. So let's look at this. Okay, we have a function. We'll take the Jacobian, which comes out fairly neatly. Okay, and you can quickly see if you write down the g as that thing, so that you don't have to write so much. So anyway, so the Jacobian, you can quickly tell that e equals to 0, and therefore they are functionally dependent. Now, having said that, we have to we calculate f2. Okay, and then by theorem, which is not 0, and which is by theorem 15, we can yank something out. Where what are we yanking? By theorem 15, actually, g is a function. Big G and f are related by the big F. So the next step, we'll follow the rules to, we're going to pull this out. Okay, and to do that, we will pick a point, which is 0, 0, and 1, okay, what end up being, just because we need a point for the theorem. And then we will we'll let this function equal to z as the proof shows, and then we're going to pull x out of there, okay, out of this thing. So then we can, or y, what are we doing here? Y, sorry. We're doing y because it's f2. So we're doing a y, so y equal to that thing, which we call phi, and plug it into the small g, which by the time which will come out with a lot of stuff, right? Because small g is long and complicated. However, we plug that into the small g and look at it carefully, you notice all x terms disappear. So convenient, right? It's like magic. And so then eventually the small g end up being just that, which we call it big F. Okay, according to the proof, because then the big F is exactly what we're looking for. And then I plugged it in to check, plug the original little f up here into the big F to make sure that it does work out, and it does. Okay, when you plug it in and you have a pile of stuff, and then eventually it looks exactly like the small g, which is great. And that is, yeah, I should show it to you again if I didn't show it clearly last time. And so that you can see that that works out very nicely. Okay, so next, let's look at problem 10. We have two functions and we need to prove uniqueness. Well, that's easy enough because we have the uniqueness of the implicit thing that we yank out of there. To show uniqueness, we only have to do this, okay? The Jacobian is not 0. And if you write the big F like this or the other way, well, who's subtracting by what doesn't matter. But anyway, they equal to 0. And then the Jacobian is a simple 1, okay? Which is not 0. And by theorem 16, we get our uniqueness, period. So that was a quick, easy thing to do. And so let's look at the words. Can't find it. What happened? Give me a second. Okay, finally, let's look at problem 11. I think we are proving a similar situation, uniqueness. So we write it down, and most importantly, we calculate the Jacobian, which again is just 1. Okay, a quick, easy calculation, and so we have proven uniqueness. However, the book raised an interesting point. That is, near xy equal to 0, 0, you can come up with delta ifs, tiny little numbers xy equal to, such where they are small, and then you can always come up with two solutions next to 0, 0. So why is that? I mean, does that mean theorem 16 has failed? Well, it did not fail, okay? Because theorem 16 only guarantees the eta neighborhood around a specific point. So the fact that there's another one next to it, we don't care. Why don't we just draw the eta neighborhood smaller and around 0, 0 so that it avoids the other solution, okay? We just draw it around one of them. And that's why theorem 16 didn't actually fail. That's just a false argument or something, a cute little false argument that sometimes happens. There is a fallacy or something. Anyway, that's why. So theorem 16 did not fail, okay? Math theorems never fail, period. And with that, we have come to the end of this section and also this chapter. How exciting. I just want to mention that we have, look at my notebook, okay? I started out this notebook, new notebook, which I was very happy about. And for when I was teaching Calculus 1, 2, and 3, I think I used roughly one notebook per course. So I thought this course should be about like all 3 courses put together. And so it should take about 3 notebooks. But so far, as you can see, I have practically used up one notebook for just one chapter. So this course looks more like maybe twice as much as Calculus 1, 2, 3 put together is maybe a better estimate, okay? Which is okay, nothing wrong with that. And it's like the last Harry Potter book is a lot fatter than the first one, so it'll take you much longer to read it, but it's even more fun, okay? So that's it.